So problem set 7 was just due a minute ago. I will put up problem set 8 as soon as I finish writing it. I'm almost done. So it'll go up later this afternoon. And we'll cover material from actually mostly today and Monday. Material on insulation. All right. So where things left off last time, dealing with phase transitions between water, steam, and ice. So I for some reason, the text widget is not working right now. No internet, so, or very little. So ask me questions live, not by text for the moment. Hopefully at this point you got a sense for the 3 phases of water: ice, liquid water, steam, and the conversions between them. Things to remind you of, that it takes energy to go from solid ice to liquid water, even if the temperature does not change. So hopefully that's not mysterious. If it's mysterious, ask me. How is it possible for the two to be there at the same temperature, and for the liquid water to grow and the ice to shrink, and they're all at one temperature? Is that okay with everybody? It is the case in every glass of ice water you've ever encountered. The two are coexisting. If no heat flowed in or out of the ice water, they would just sit there exactly as they are, with virtually no evolution. I mean, you would not lose ice in favor of water or vice versa. They would change a little in shape because they really are exchanging molecules. And so there will be a gradual change in the shape of the ice relative to the water. All right? If you do add heat to the mixture of ice and water, the heat goes not into raising the temperature, but into melting the ice, paying the latent heat of melting to turn the solid ice into liquid water. All right? Water and steam, they can coexist. They can coexist over a much wider range of temperatures. The way they handle that is that at low temperature, they coexist while the steam is at very low density. There are very few water molecules in the steam per liter. So that even though at low temperature it's very rare, relatively rare, for a water molecule to break free of the surface of liquid water, it's okay because one water molecule rarely lands from the steam on the water because the density of the steam is so low. So they're a matched pair. At higher temperature, you get a different matched pair. That is, the water molecules break free of the liquid water more often, so they're leaving more often the water. They're also landing on the water more often because the steam becomes more dense when it's in equilibrium with the water. Is that okay? Lastly, the ice, and so that's potentially condensing and evaporating. If they're out of balance, if the landing and leaving are out of balance, then you get evaporation or condensation. If they were in balance and you add extra heat, you tend to drive the liquid into the gas. Liquid shrinks, gas grows. Take heat out, you go the other way. In each case, there's energy being, the energy that you're putting in is not going particularly into raising or lowering the temperature. It's going into freeing up the water molecules or sticking them. All right? Lastly, the solid and gas, these two do also exchange molecules. The water molecules can break free from the solid, head off in the gas, and they can break free of the gas and land on the solid. And those are, if they're actually happening, if you're losing solid in favor of gas, that's sublimation. If you're gaining solid in favor of gas, you're at the expense of gas, you're depositing, or it's frost. All right. Where I really more or less left off was trying to look at the special phase transition or special example of evaporation, which is known as boiling. So where does that fit into the theme of things? If you've got a pot of water with an open surface, so the water ends and then gas or empty, sort of semi-empty space begins, the water molecules can leave the liquid surface for the air above. And they do that based on how often they get enough thermal energy to break free. So as the temperature goes up, they break free more often. And they land on it, of course, depending on the density of water molecules in the air. So assuming they're not very dense and the temperature is high enough that the molecules are breaking free often, you gradually lose liquid water for gaseous water and the water evaporates. Well, The rate at which the water evaporates is limited because you got only so much open surface. Not very much, ultimately, this much. But if you could add extra surface, you could get faster evaporation. So you could take the whole thing of water and just spray it into the air, make it evaporate faster. And that is one way people use to evaporate liquids faster, is spray them, give them more surface area. But the one that's more familiar and more common is you allow the water to evaporate not only from the top surface, but into bubbles. And they could be air bubbles if you blew air through the water and you provided that internal surface to allow water to evaporate from liquid water to gaseous water inside a bubble. But the more interesting arrangement like this is boiling, where the bubbles are not air bubbles, they're steam bubbles. So they're bubbles of the water vapor itself, dense enough to be there, to exist in the water and remain stable against the crush of atmospheric pressure. So if you could have a steam bubble in water, regardless of temperature, water could evaporate into that steam bubble. In reality, at any temperature short of 212 Fahrenheit or 100 C, the steam bubble doesn't survive long enough for this to be an interesting effect. Because the steam bubble is pushing out, atmospheric pressure is pushing in, the steam bubble doesn't have enough density to push out as hard as atmospheric pressure pushes in. The steam bubble just gets smushed. So yeah, you got it briefly and then it gets crushed out of existence, gone. So that whole story is pointless. But once you get to 212 Fahrenheit or 100 C, and these are approximate numbers, they're empirical numbers, ones you measure, they're not predicted by some sort of theory. And they're local, they're to Charlottesville I'm talking about. Once you get to that temperature, if you have steam at that temperature in equilibrium with the water, liquid water, the two of them can coexist, and the steam is there, not getting bigger or smaller, and the water's there, not getting bigger or smaller. That steam bubble has a lot of pressure because it's pretty dense stuff. It actually has atmospheric pressure. So there's enough gas packed in there to hold the bubble stable against the crush of atmospheric pressure. And now it's possible for additional water molecules to break free of the liquid, go into the steam bubble, and make the steam bubble get bigger, grow. And that's boiling. So when you watch water boiling on a stove or in a hot pot or something like that, what you're seeing is you're seeing steam bubbles that already exist, and I'll come back to where they came from in a minute. You're seeing steam bubbles that have dense enough steam inside them. And I also want to point out, steam is a transparent gas. You can't see it. When you look at the mist coming out of a hot water pot or something kettle, you're not looking at steam, you're looking at condensed water droplets that came from the steam. The steam itself is just invisible. So the bubbles of steam inside the boiling water are similarly invisible. You just see, they just look like bubbles of empty things. Any old gas, any old non-colored gas. So they are growing by evaporation, and because now the surface area available for evaporation is so huge, it's not just the top surface anymore, it's the top surface and every surface of every bubble in the mixture. They evaporate like crazy. The evaporation is now just way stepped up in speed. And among the consequences of that are the fact that it's very hard to drive the temperature of the water much above the point at which this happens. So if you heat water on a stove, starting at warm water level, just make it warm water, as you heat it in ordinary room air, there is evaporation. So some of the heat you're putting into it is going into raising the temperature, and some of it is going into evaporating the water, into breaking the water molecules free of each other and sending them off as gas. So it's a split. The temperature is not going up quite as fast as it would go up if you block the surface. No water molecules may leave. If you cover the surface, I don't know, aluminum foil, saran wrap, oil, something that blocks the surface so there can't be evaporation, pot lid, then every bit of heat you put in there will go into raising the temperature. Because water molecules are forbidden to break free. I'm sweeping little details under the rug, but that's pretty good. When you open the pot, uncover the water, okay, now you got evaporation, so some of the heat you put in isn't going to go into raising the temperature. It's going into evaporating water molecules and paying the latent heat of vaporization. What the balance is between the two depends on the situation, but it's, tens of percent of one and tens of percent of the other probably. So as you keep putting in heat, it gets hotter and hotter because a good fraction of the heat that's going in is going into raising the temperature. Once you hit the boiling temperature and boiling becomes active and rapid, now you're in a different situation. It suddenly becomes very hard to raise the temperature much because all of the heat, 99 point something percent of the heat is going not into raising the temperature, but into breaking water molecules free of each other and setting them off as a gas. And that puts sort of a stop on the rise in temperature of the water as you heat it. Hit boiling, suddenly you can't go hotter. And we use this for cooking all the time. Boiling water has a particular temperature. It is location dependent, and I'll come to that in a minute, but it's a pretty well fixed temperature. It's one of the few that historically people had that was sort of regulated. It was self-enforcing. You always had the same temperature. Every time you had a pot of boiling water, it's the same temperature. So you could cook in it and know how things will cook, like eggs. So when people put eggs in boiling water, what you're really doing is you're putting an egg in an environment with a well-defined temperature that we know and love, and it's been the same since last week, and the week before, and the month before that. And you know how fast things cook in that specific temperature environment. Is that okay so far? If you change altitude, and to some extent weather, if the atmospheric pressure changes, that changes the situation, because once the atmospheric pressure changes, the density of steam you need in order to balance off the crush of atmospheric pressure changes. If the atmospheric pressure decreases, for example, for whatever reason, you don't need the steam to be as dense. So the water doesn't have to be as hot to have stable steam bubbles anymore. All right? So reduce the atmospheric pressure by going, in the mountains, or some real mountains, serious mountains. Blue Ridge is a good start, but go to real big mountains, and the temperature at which water boils will drop significantly because the atmospheric pressure is just weaker. The bubbles are stable at lower temperature, and so that's why a lot of people who live at altitude know that you have to cook differently. The egg that used to boil properly cook properly in boiling water back at sea level now doesn't cook in that same amount of time. You got to cook it longer, or you got to do something. You got to use a pressure cooker. And pressure cookers are related to this. And if I forget to think about them, let me know. I think this guy may finally have made connections. What else? Oh, okay. So at high altitude, not only do things cook differently in boiling water, but a lot of recipes have to be changed because almost every recipe involves water somewhere. It's just part of our life to such a great extent that it's in there. So there are high altitude recipes for many products. You go look on the shelves at a supermarket, you'll find some fair number of boxes that will say high altitude recipe for baking, for example. Things just cook differently. The water evaporates, boils more easily. All right? Extreme case of this is if you really start deliberately manipulating the atmospheric pressure. I'll do pressure cooker first because something that just popped in my head a moment ago is if you package the pot so that it can't exchange gas molecules in or out, it keeps the water molecules confined, you can cause the pressure to rise inside the pot. It's going to be a mixture of air and water vapor, but it doesn't matter. The result is the local atmospheric pressure, in air quotes, might be twice atmospheric pressure. If that happens now, it's harder to get a water bubble, a steam bubble, to survive in that high pressure environment. You have to make the steam denser. So that means you have to heat the whole system hotter to have high pressure steam be stable against condensation. You want to keep the water molecules in the gas and not have them condense out by landing too often on the water. So in a high pressure environment like a pressure cooker, water boils at a higher temperature. And you can heat it right through 100 degrees Celsius, or equivalently 212 Fahrenheit. You can go right up to, I don't know, what, at 2 atmospheres, I'm not sure what the pressure is, but it's, it's going to be something like 230 degrees Fahrenheit, 120 Celsius, something in that territory. But this is why people cook things in pressure cookers. You go to a pressure cooker, water boils at a higher temperature in that higher pressure environment, and you can heat things hotter and cook them faster as a result. All right? For sterilizing stuff, boiling water sterilizes pretty well. It kills most germs, not everything. And so when they really want to put stuff in an environment that kills all the germs, they put it in essentially a pressure cooker, known as an autoclave, that raises the temperature higher by boiling water in a higher pressure. So I want to do the opposite. I'll boil water in lower pressure, but going to the mountains would reduce the pressure by a factor of 10%, 20%, 30%. Let's go for 100%. And so the idea is this. We've got a container of water over here, and it's just at room temperature, right? No, not really. It's just ordinary room temperature water. And right now it's evaporating off of its top surface, as usual. And I will risk going here to zoom the camera in there. Okay, the camera is looking at it, and I will dim the lights and risk, I don't know whether it's more visible or less visible. I'm going to take the air out around that water. And in doing this, the water will begin to evaporate pretty aggressively because there won't be much landing. The landing and leaving will be entirely in favor of leaving. There's no gas anymore, so there won't be much landing. And a lot of water vapor will be coming through these pipes into the pump. And to keep them sort of out, keep that water vapor out of the pump where it gets in the oil and the oil in the pump doesn't like it. So I will trap the water on a very cold surface. I'm going to force the water to deposit and form frost on a surface inside this pump with the usual favorite liquid. Okay, stop bubbling here. Get the job done. All right, good enough. All right. So I'm going to take the air out now. Here we go. So as we do this, we make it more and more possible for water to boil. That is, for a steam bubble that is in the water to exist stably against the crush of now very low atmospheric pressure. It's pretty easy to exist. And it can grow then by evaporation. We're not quite there yet. Hopefully in the near future we'll hit boiling. It's about, yeah, it's close. It's the literal watched pot. But the weird part about it is still at room temperature. In fact, because the water is evaporating, it's using up some of its own internal thermal energy to evaporate, and it's actually cooling down. So that water, when this whole story is over, will be at room temperature or below. Can you see the bubbling starting? We ought to get a full rolling boil going in a minute. So whatever bubble is present has no problem existing because there's just so little pressure pushing on it. Bubbles are fine, even light fluffy bubbles. So these bubbles, there it goes, nice rolling boil, but it's at room temperature. It's just possible because we're not pushing in, so the bubbles are stable. Okay? And there are various toys and gadgets that are based on this idea. You can trap water and water vapor in a container with no air and make it so it boils whenever you have a temperature difference across it. So lots of old parlor toys. Not very interesting in the days of apps. Okay, so I'm going to stop the water from boiling, and just so you know, nothing really changed in the temperature. I will let the air back in and show you that it still doesn't burn my fingers. And actually, it's cold enough that water condensed on the glass. You can see the water vapor that was present in the dome. So it's still what room temperature? Nothing up my sleeve. Okay. You guys are easily pleased, I think. This late in the semester, it's like, yeah, good. Okay, so that said, let me show you another extreme example. I'm not going to show you live, I'm going to show you a video. And here's the story behind this. When I'm showing you boiling, so boiling, again, it's just glorified evaporation into bubbles. If you got a bubble, you can evaporate into it. But what if you don't have the bubble? In other words, so where did the bubble come from? And it turns out that in normal boiling, the bubble has to, in any boiling, the bubble has to start somewhere. And the bubble typically starts in a metal pot on the stove in some nook or cranny in the damaged, imperfect surface of the metal, or a place where it's particularly hot. If you've got a little bit of trapped air, what is known as a permanent gas, something that doesn't condense the way water does at room temperatures, you can have the bubble grow out of that little empty spot, a little cave. And I call those little places where the bubbles come from is like bubble nurseries. And the process that they're doing is what's known as nucleation. They're creating a seed bubble, the first little nugget of bubble into which the water vapor can then evaporate. Water can evaporate as a vapor and make the bubble grow. And this process of seeding out bubbles is very familiar to you, not necessarily from boiling water, although it is in boiling water. If you watch the water bubbling off out of a stove top or something, you will see the bubbles typically come from the same place over and over and over. More familiar is the bubbles of carbon dioxide coming out of solution in your favorite beverages, sodas and beer and champagne, if you're of that, right? Watch where the bubbles come from. They don't just like appear in the middle of the liquid, because creating a bubble, it's very similar physics. The bubble, once formed in a fluid overfilled with carbon dioxide in solution, the carbon dioxide loves to come out of solution and become a gas, much the way water likes to come out of water liquid and become a gas if the situation is hot. So those bubbles of carbon dioxide grow by essentially evaporation of carbon dioxide out of the solution. But you got to get them started. And where do they start? They typically start at some little piece of crud on the surface of your glass. So you see a stream of them coming out of the same spot over and over. This is surely familiar, or you're not paying attention. And as a physicist, I pay less attention than most, so I've seen it, okay? Sets the state, sets the scale, the bar is low. So where do the bubbles come from in boiling? Typically from defects in the pot or from junk that was in the water. What happens if you don't have any defects in the pot or junk in the water? If it's really clean, and clean doesn't mean that it has to have no, it can be soup. It doesn't have to be pure water. It just has to have no places where bubbles can form. So things that are totally in solution or totally wetted with water. So there's no gas there sitting around popping out bubbles. In that case, when you hit boiling, the water can boil, meaning it's got enough thermal energy, there's enough thermal energy kicking around to cause evaporation into a steam bubble and for the steam bubbles to survive against the crush of atmospheric pressure and grow. But if there are no bubbles, you don't get, that whole thing doesn't happen. You don't get boiling. You just, the heat you put in continues to increase the temperature. So the water becomes heated beyond boiling. The names for this are my preferred term for it is called superheated. It can also be called overheated. It's hot enough to boil or hotter than necessary to boil, but there are no bubbles in it, so it's not boiling. So far, so good? That said, God, this is how many years ago it was, a long time ago. For complicated reasons, I became really good at superheating water. Where do you do this? You can do it with a glass or glazed container, glazed mug, in a microwave oven. The heating it's not conventional heating where you've got a hot object and a cold object and heat flowing from hot to cold. Microwave heating is somewhat different, and a glazed or glassy surface has no structure in it. And it is possible with a little skill, terrible skill to make it so the water stops boiling. You take it right through boiling. And I got really good at that. And as part of that, here's a video associated with that. Now where's it? Main, there. Is this up here? Okay. Ooh.
From ABC News, this is Primetime Thursday.
We're going to start tonight with a report on something that you use every day, probably without thinking about it, the microwave. Tonight, we're going to show you how it can cause a dangerous explosion in your kitchen. This is actually a story suggested to us by one of you in a letter over the internet. And it involves a bizarre phenomenon. Before you use your microwave again, you really ought to see what Chris Cuomo found in this Primetime Owner's Manual.
At about this time last year, Patty and Dave Long of Naperville, Illinois, were preparing for Easter.
It was Good Friday. The kids were off school.
Time to make Jell-O Easter eggs. Patty put the water in the microwave for 3 minutes to boil, but something seemed wrong. No bubbles.
So I hit the add 30 seconds, and I stood and watched it. But it wasn't boiling, and I thought, well, you know, it's got to be boiling. Something has to be wrong.
Patty had been using a microwave for years. She was confused.
So I opened it up, I brought the container out, and I just kind of brought it down like this. So I was going to touch it with my right hand, and before I got my right hand there, I heard this like whoosh, and I got hit with all that water into my face.
It exploded.
It exploded like a bullet, and it just hit the ceiling, too. There was no water left in the cup.
Patty had first and second degree burns all over her face. Even worse, the corneas of her eyes had been scalded.
The whole eye was burned, and they were swollen on the inside, so it was blocking some of the vision because of the swelling inside the eye from the heat.
Were you afraid that you may have gone blind?
Yeah, I was afraid I'd never see my kids again.
It would take 6 months of treatment for Patty to fully recover her sight. Still, no one could explain what had caused this accident.
It really wasn't until I got home and saw the water on the ceiling that I really understood that something strange had gone on here, something that I'd certainly never heard of before.
People who have these sorts of accidents are probably reluctant to talk about them because it seems so bizarre and so unlikely. Who would ever expect water, the safest thing we can imagine, to come up and hurt us?
Let us show you what happens in slow motion. Water heated past boiling, more than 212 degrees, can erupt. Mary Ann Ostermeyer says it happened to her, too. A middle school teacher in Southern California, she'd been using a microwave oven for nearly 20 years. She says she had been cooking homemade soup on low power for 50 minutes. Remember, low power.
Well, I ended up grabbing 2 hot pads. I opened up the microwave. I had one on the handle. I took and poured a small amount of soup in the cup. Then I reached in to the utensil drawer. I picked up a fork. By this time it was sitting down. I took the edge of the fork or the tip of the fork, put it in, and the next thing I knew, there was this incredible sound like a gunshot or a backfiring of a car. And immediately there was an explosion. I mean, the whole thing just exploded.
What was the extent of the injuries?
First-degree burns on the face, first-degree burns on the wrist, and on the top section of the chest region. First degree, the lower quadrant of the left breast, third-degree burns.
Third-degree burns.
Yeah.
Both Mary Ann Ostermeyer and Patty Long's husband, David, searched for answers and found them here, a website by University of Virginia physicist Louis Bloomfield. It features video of an experiment that looked painfully familiar.
I probably get more questions about microwave ovens than all the other questions I get combined.
Professor Bloomfield says there's a simple scientific explanation for how these kinds of explosions can happen.
You're used to having water or liquid boil when you heat it above a certain temperature. But there are occasions, and they're more frequent than you'd expect, in a microwave oven where the water goes to or above boiling without any bubbles forming. That's a phenomenon known as superheating.
Superheating.
Yeah, it's hotter than it should be for normal boiling to occur, and yet it doesn't boil.
Here's why. Something has to start the bubbles forming. Any little imperfection, like the texture of a metal pot, will do.
But in a clean glass container, heated by a microwave, there's really nothing to trigger the bubble formation. It's a process that physicists call nucleation. That bubble formation never starts.
So Bloomfield says, even though it may look unheated, it can actually be superheated.
Now, what does that mean exactly if water's superheated? It's just hot? How's that dangerous?
Well, it's almost like a bomb once you've got it superheated adequately, because anything that triggers the boiling, once you've reached that temperature, will cause catastrophic, very sudden flash boil.
Now, can you test this? Can we show it?
Well, we've got a container of
We tried so hard to get a really good
water here with
explosion.
some red food dye in it, and a little bit of fat floating on the surface.
And I wore
of
the
oil.
coat because it
Like
took
it
me
were
so
soup.
long to
We
find one in
microwave the
Southern
liquid on high
California.
power for about 3 minutes. There isn't
No
a
one
flash
wears them.
reaction every time, but this can be dangerous. Don't try it at home. Look what happened to us.
Ready? Let's go.
Bloomfield says all it can take to trigger an explosion of superheated liquid is for something like a fork to break the surface. Then, watch out.
You don't think that when you go into your kitchen, use a microwave, which almost everyone uses.
Okay. Yeah. Yeah. So I learned how to do that really well. Although, of course, while we're filming it in this one with Chris Cuomo, we couldn't get it to really go kablooey. But later, as you can see, this is a while ago. My hair is a slightly different color. But there was a film crew out of Washington in our house with our microwave oven filming this, and they had the camera on very high frame rate, short exposures to try to really get the explosion beautifully. And the camera's in there, and I'm blasting away at the stuff for 30 seconds past boiling was my goal. I had it set for 30 seconds past boiling. I can tell you more about the issues here, but at 28 and a half or 29 seconds, we're hovering there ready because I'm going to open the door and stick something in it and watch it go kablooey. 28 seconds, it went kablooey on its own. And in a single frame of their video, it went from being like, there's the door, there's the liquid in the container, everything's good, to where'd the door go? Where'd the liquid in the container go? What's all that smoke and steam around? And why is that guy screaming because he just got hit in the head by the door of the microwave? That being me. Ah! Yeah. The explosion is can be pretty crazy. That was one of the last times I did it because I'm getting to the point where I can kill myself doing this. The idea is, it is possible to systematically kill off the little bubble nurseries, and that's what I got good at doing, was I could cycle it back and forth between boiling and not boiling until there were just none of these little nucleation sites to create the bubbles. And then once that was gone, once you had it clean and it could not boil, then I could heat it essentially forever and get it as hot as I wanted. And I was going for 30 seconds of past boiling, with the idea that would make quite a good but not super dangerous explosion. Well, it was up there. Public service announcement time with this then. I hope you understand the physics aspect of why it does this. That boiling is something that you're so used to seeing at 212 Fahrenheit or 100 C that you just take it for granted, but there are ways in which you can kill it off so boiling doesn't happen, then you just take the water past boiling. And you've all seen this to some extent if you've used a microwave oven to heat your coffee or tea or something like that. If you just mildly superheat it, which is relatively easy to do, when you put stuff in it, like you put a tea bag in it or you sprinkle in powder, whatever, it will sort of bubble amusingly and splutter around on the counter. So what happened there? Why did it just sort of splatter around the counter? And surely some fraction of you have seen this. It's when you take it way past that it becomes dangerous. And the point is, the public service announcement part is, if you have heated a liquid in a glass or glazed container in the microwave oven, and you know that you've heated it long enough to boil it, and it's not boiling, be a little careful with it. Because for the most part, if you don't try, you won't get it dangerous. But you can get it dangerous. And these women both did. They got it to the point where it was way past. And they may have accidentally imitated the techniques that I got good at doing, of killing off the bubble nurseries. And once that happens, then they're really in trouble. All right? So, be a little bit careful with the water. Are pots made so the bubbles are allowed to form? And the answer is not really. It happens so easily that it's not much of a problem. The effect is one that shows up often in, I think particularly in a chemistry lab. If you heat water carelessly in glass containers, and particularly if there's water in a mixture of things like oil, you can get the water to go beyond boiling and not boil. And when it does finally boil, people refer to it as bumping. There's a splutter, and sort of a puff, and it blows the liquid out of the container to some extent. So people often use what are known as boiling chips in chemistry when you're heating liquids. And you want it to be boiling, and you want to make sure the boiling is sort of smooth and not erratic and dangerous and burpy. You put the boiling chips in, and they're bubble nurseries. What's their point? They have little nooks and crannies that trap permanent gas that allow for the creation of bubbles. So boiling is smoother. Without those, you can get bumping, which is the throwing the liquid out. And if you get really good at it, then you blow the whole thing up. All right? Any questions? All right. Last tidbits about water, steam, and ice, just things to bring up. If you add to the water anything that kind of ties up the water gets involved in dissolving. So sugar, salt, baking soda, just many things from the kitchen. When you put them in there, because they tie up the attention of the water molecules, they make it harder for the water molecules in the liquid to exchange with the other phases, either gaseous or solid. And that means that the balance between landing and leaving is messed up. And the result is, it is harder to boil the water. It slows the evaporation down and consequently makes the boiling temperature higher. And it also slows the freezing down and therefore makes the freezing temperature lower. And you've seen this. If you start adding a lot of sugar, in particular, to water, the temperature at which that mixture, that solution boils at, goes higher and higher and higher. So if you ever made candy, and this is a major part of candy, is these various stages of water, sugar mixtures and their temperatures. They go right on up to too hot, dangerous, caramelizing. And you've also seen that this bit, when you start adding things that dissolve in water and try to freeze it, it gets harder and harder to freeze. And where an example where this shows up is in melting ice during the winter with salt. When you throw salt on the ice, what you're really doing is you're stabilizing the liquid phase relative to the solid phase. Because once the liquid forms, the salt goes into solution in it, ties up the water molecules, busy trying to keep the salt dissolved, and they make the water phase more stable, harder to make the ice out of it. And so to get the ice to form, you got to go to a lower temperature to make it to get that coexistence situation going. So this is why if it's 28 degrees Fahrenheit outside or -4 Celsius, and you throw salt around, it melts the ice because you've made it easier for water to exist, harder for ice to exist. The ice just melts in favor of the water. If it gets cold enough, though, you need more and more salt to do this, and eventually it doesn't even work. All right? And it isn't special about salt. It's that the salt goes into solution is the key thing. There's issues of concentration that do matter, but you can melt ice with things that, other than salt. Anything that goes into solution will work. Maybe some better than others. But you can melt ice with sugar or baking soda or whatever. All right? You can't do it with sand because sand doesn't go into solution in water, and so it has no effect on the melting temperature of ice. All right? I think that'll do it. So let me now start setting the stage for the next topic, which is clothing insulation and the climate. It's really nothing new, or very little new. The issue is this, that in wood stoves and in the problem set about cooking, for example, and the water, steam, and ice, it's a lot about moving heat around and trying to move heat around. What about if we try not to move heat around or to not move heat around, to keep it in place? So that's the purpose of insulation and all of insulation's relatives. And to do that, you just pretty much want to systematically block off the three mechanisms of heat transfer, and then also the ones associated with, say, water and steam and ice, the phase transition stuff. So you want to get rid of thermal conductivity, you want to get rid of convection, you want to get rid of radiation. And stuff that just to show you stories, let me put this back there. Probably one of the best insulating systems in existence is a device like this known as a dewar, named after a person dewar, D-E-W-A-R, which I think is the same as a whiskey, or I don't know. I can't distinguish any of those things from one another. Anyway, liquid nitrogen certainly doesn't like to exist at room temperature. I mean, it will not exist at room temperature. This is way too hot for it. But it can exist in a container like this because this container does a great job of getting rid of two of the heat transfer mechanisms. So the room's hot, the liquid nitrogen is cold. We're trying to keep heat from flowing into the liquid nitrogen. And this container is a double-walled container with a vacuum in between. And years ago, it was totally sealed in glass, but after breaking it enough times and ruining the internal vacuum, Al and his team put on a system where they can remove the air whenever they want to, and it's a better arrangement. In any case, here's the idea. Heat can't get into the liquid nitrogen through this system because the outer wall and the inner wall are only connected by a narrow rim here in the middle, and so conductive heat transfer is pretty pitiful. It has to work its way through the entire thin sheet of glass, around the corner, and then down into the liquid nitrogen. It doesn't happen very fast, so there's a slow leak of heat in through the glass. Heat can't get in by way of convection because between the two walls there's no gas to convect. It's just empty space, so nothing moves that way. And also, when you've got a cold system like this in the midst of a hot system, natural buoyancy doesn't cause trouble either because the air right above the liquid nitrogen is being cooled. It becomes more dense, and it's the opposite of buoyant. It descends. It wants to sit there. It's happy there. There's no natural buoyant effect that would lift it off and send it around the room. If this were hot, if we put hot stuff in here, we would have a problem. Natural buoyancy the air would heat up, it would rise, go up, and be replaced by cold air. We'd lose a lot of heat. And where I'm going with this idea is that we've all seen in grocery stores the freezing containers that are compartments, frozen foods that are just sitting in a big frozen food bin with no top on it. Like, doesn't that have terrible problems with keeping it cold? And the answer is no, because natural convection does not move heat effectively in this situation. The cold food is on the bottom where it cools the air, which descends to the bottom, which descends to the bottom, which descends. It sits there. It's the reverse of my boiling water at the top of the test tube trick of last time. So if you put out cold foods in these bins, they're pretty well insulated. Air itself is a crummy thermal conductor. If it doesn't convect, almost no heat moves. It doesn't convect, so it's pretty great. Hot food, not so good. So hot food containers like that, they'll bleed heat like crazy. So this guy shuts down conduction and convection. It does not shut down thermal radiation, though. The two walls of this container, both of which are glass, are essentially jet black in the infrared. And so they are exchanging heat by way of thermal radiation. Each wall is seeing the other wall, and the outside one is hotter than the inside one, so it's radiating more thermal energy at the inside wall than the reverse, and there is heat flowing into that container by way of thermal radiation. Okay? What can you do? You can coat the inside surface entirely with a shiny material, and that's what this is. So this dewar is, it's fun, it's great. This is another one, essentially the same idea, but it's made visible. In order to allow you to see the liquid nitrogen sitting in there, they have not put the shiny surface in there. if these were being used to keep stuff cold for serious work, you'd want to mirror the inside surfaces so that the two surfaces see their own reflections as far as thermal radiation is concerned, and they do not exchange thermal radiation. So that's this guy. This guy's obviously not a very good one for looking at anything because you can't see through it, it's mirrored. But it will certainly keep liquid nitrogen around longer. And that's what it does for a living. Okay? Apart from that, so back to insulation stuff. Let me try to deal with most of the insulation story. 4 minutes, I probably can do it. What I can't do is climate. I'll do climate on Monday. So the main insulator that we use in everyday life is air, the best insulator. The gases are much worse. They have terrible thermal conductivities. They're not all identical. Some are better than others. But for the most part, gases do not conduct heat well at all. If you can keep them in place, they will not carry heat very well at all. Vacuum would be better. Empty space would be better, but it's unrealistic in almost every circumstance except when you can like pump it out between two walls of a glass container. So that's why we wear clothes for the most part, to keep, at least for the thermal aspect of wearing clothes, is we trap air. They're all designed for that. And it is possible to, knowing that, things that you can do that spoil the insulation of clothes, don't pack them too tightly. So some of my questions that I'm not using these days. If you overpack, for example, down into a coat, so coats are often sold with a certain amount of down in them, and you might think, well, if you bought that same coat with twice as much down, it would be twice as insulating. And in fact, it would be less insulating. Because as you start to pack more and more of the down in there, you're now looking at the thermal conductivity of down itself. And down itself is probably not a good conductor, but it's not terrible. Air is worse. So the down's purpose is not to be the insulator, it's to trap the air using the familiar viscous drag forces. Air doesn't flow around fine particles very well, any more than fine particles flow through air very well. Dust gets suspended, right? The dust and the air talk to each other, and they don't like to move relative to one another. The same with the fibers of most of our clothing. Even our hair, air has trouble moving relative to those fibers because of viscous drag forces. So shut down the movement of air, and now you have air, the insulator, being unable to conduct heat, being unable, because it's terrible at it, unable to convect because it's held in place by the fluff, and you can get huge temperature gradients without very much heat flow. That leaves radiation. This is aluminum oxide, what's called alumina. It's an alumina fluff. Housing insulation is generally, a lot of it is glass fluff, glass fiber in the walls. This is cellulose fiber. Basically, they're all just fibrous things to trap the air. The insulation is air. Everything else is there just to keep the air from doing convection. And this stuff is so good at that, and it's so heat tolerant. How do you keep this guy on? I don't know. I should be able to hold this in my hand. My goal is to get the penny red hot without getting my hand red hot. Not only did I get the penny red hot, but I melted it. It's now a melted penny. And my hand is kind of like, was there some heat there? No, nothing. Okay? So the insulation, I would not try that with a block of alumina. A block of the same material, not fluffed, bad idea. It's not a good conductor of heat, but it's good enough that I would now have no fingerprints. But this is, that fluff the air is such a good insulator. So anyway, most insulation is air. Cut down the convection. Thermal radiation, I'll talk about it. It's a long story potentially. So we'll deal with that on Monday. Otherwise, have a good weekend.